Nuclear reactor design part 2. I finished the first session by referring to the 3 Mile Island incident and the Chernobyl incident, and these two incidents caused a hold-up in the development of nuclear power because a lot of contracts were cancelled in the wake of these two disasters. First of all, it's important to reiterate that the Chernobyl disaster was not an accident. It was a result of a deliberate action that somebody took. They were trying to explore the operating parameters of the RBMK, and they weren't adequately supervised, and somebody did something stupid, and that was what happened. And the other thing to emphasize is that there is nothing inherently wrong with the design of the RBMK reactor. Anatoly Alexandrov, the bloke who designed it, is an eminently respected nuclear scientist, and in fact the Russians built an RBMK reactor for the Finns in Finland, and the Finns said thank you very much, and they partially dismantled the control system to this reactor and rebuilt it according to Western fail-safe principles. And they've run that reactor for the last 30 odd years without any trouble at all. Now, in Russia, the Chernobyl incident was just one of a series. There was an incident at Ignalina in Lithuania in the early 80s, and in 1990 there was another incident at Sosnovyj Bor on the Gulf of Finland, another RBMK with the release of radiation. So there is nothing inherently wrong with the design of these reactors. It's the control systems that gave the problem. So where are we now? Well, the first generation of reactors in the UK were the so-called Magnox reactors. They were called Magnox because the fuel rods were encased in a magnesium non-oxidizing alloy, hence the name Magnox. And I don't know, 11 or 12 of these things were built, starting in the 50s and running through to the 80s, and they've now all been closed down, and they're now in the process of being decommissioned, in some cases dismantled. The next generation of reactors to be built in Britain were the advanced gas-cooled reactors. 7 or 8 of these were built. They are graphite moderated, gas cooled. They're cooled by carbon dioxide gas. Now, the advantage of using that design is that you can run the reactor at a higher temperature. And since basically, it's a heat engine, the normal principles of thermodynamic efficiency apply. So the higher the high temperature side of the business, the greater the efficiency. So the fact that you can run these things hotter than the Magnox ones is an advantage. The thing with because they do run hotter, they could no longer encase the fuel rods in magnesium alloy, and I think they're now sheathed in stainless steel. Now the consequence of this is stainless steel absorbs more neutrons than the magnesium, and so whereas the Magnox reactors would run on very low, almost non-enriched fuel, if you're going to run the AGRs, the advanced gas-cooled ones, you have to use fuel enriched to 3, 4, 5% because of the fact that you absorb more neutrons due to the stainless steel sheathing. Now, these reactors were due to be taken out of commission starting in the next few years and running up until the early 2020s. They, however, a decision has been taken that they're going to try and run them for an extra 10 years. It's all subject to a safety assessment and so on. And of course the final reactor to be built in Britain was a pressurised water reactor at Sizewell B, which came on stream 30 years ago in 1984. And that has a design life of about 50 years, so that will run for another 20 years at least. Now, while reactor building came to a halt, the nuclear physicists, nuclear engineers, continued to try to dream up improved reactor designs, and they came up with a number of designs: the boiling water reactor and the heavy water pressure reactor. These are all water-cooled, water-moderated reactors. Again, they can run at higher temperatures, so they're more efficient. These designs are now being built in China. The Japanese built a lot of reactors. In the wake of the Daiichi Fukushima disaster, they've closed a lot of their reactors down, but they are going to restart many of them, because you can't close 50 nuclear power plants down and not notice the reduction in electrical power. And then of course the Fukushima Daiichi disaster, a lot of lessons have been learned from that and are being learned from that, because they're still finishing the investigations into what went wrong. And the Hinkley Point C reactors, which are going to be the next ones built in Britain, will be incorporating some of the lessons learned in the Fukushima Daiichi reactor. Now, I've mentioned the fact that we can run these reactors at higher temperatures and therefore achieve a higher efficiency. That's not the only advances that have been made. We certainly in Britain, in the 1950s, in 1959, they built a fast breeder reactor at Caithness, up near John O'Groats, and gained a lot of experience it's called a breeder reactor because you can breed more fuel. So the principle is that you can build your reactor, and of course when it's in operation it's spraying out neutrons, fast neutrons. If you surround the reactor core with spent fuel, these neutrons will crash into that, and you can generate plutonium-239, which is fissile. So in other words, instead of throwing the spent fuel away, you bombard it with fast neutrons and breed some more fuel. So you don't have to throw the spent fuel away, and you don't have to mine more uranium. Now, believe it or not, we've got to a situation now where nuclear engineers talk about open and closed systems. An open system is one where we feed stuff in and some of the rubbish gets dumped. You know, classic human operation. But the closed system is more as nature does things. In other words, things are recycled. And in the closed system, you breed more fuel and avoid the necessity for throwing spent fuel away, disposing of it, and avoid the necessity for mining more uranium. So that's one of the developments that's come in the last few years, and some of the objections of the anti-nuclear lobby, some of these objections have been negated by these developments. Another interesting development is the plutonium is a metal, an element that doesn't exist in nature. It's entirely man-made, and since 1945, when the Americans produced the first plutonium for their bombs, we've now accrued a stock worldwide of 2,000, 2,500 tons, perhaps 3,000 tons tops. In the UK, we have a stock of 120 tons of weapons-grade plutonium. Now, of course, this is nasty stuff. It's toxic, and it can be used for weapons, which aren't nice. But a very recent development I've seen announced is the PRISM reactor. Nuclear engineers have designed a reactor called the PRISM reactor, which can burn fissile plutonium to generate electricity. So we don't have to dispose of this very toxic substance, we can actually use it to generate power. And since it's very expensive. At the time when gold was worth £6.5 million a tonne, the cost of weapons grade plutonium at that time, which is quite a few years ago now, I did the sum, was £300 million a tonne. It's very expensive material. So having produced it at that enormous expense, it seems a shame to throw it away or let it fall into the wrong hands if we can actually use it to generate electricity. So the developments in reactor design, and there have been many, centre on operating at high temperatures, operating with more thermal efficiency, reducing the amount of waste and breeding more fuel, and avoiding the necessity for disposing of this nasty nuclear waste. So the nuclear industry in future, the people who bang on about the problems of waste in the nuclear power industry seem to imagine that the industry stands today where it stood back in the 1950s and 60s, and that's not true. We've moved on. We have actually developed a lot of improved designs, and that is the current picture at the moment. So the future for nuclear power is quite bright. It doesn't carry the same environmental penalties that it did 50 years ago. It's more efficient, and certainly in terms of cost it compares very favourably with wind power and various other these so-called renewables, which are all very well, but they cannot supplant our existing sources of power. Wind power is okay, you can feed it into a grid, so if you don't want to use it, somebody else can use it if you connect your grid up to somebody else's. That's what the Danes did. They connected their electricity grid to the Norwegian grid. They've got a big row of wind turbines off the coast near Copenhagen, and when they don't need the power those generate, they feed it into the Norwegian grid, and when they need more power, they can take power from the Norwegian grid. So it's not true that because these things won't generate baseload power, they're no good. That's not true, because you can feed them into an integrated system. However, it is true that if the wind doesn't blow, you get no power. And one of the big advantages of nuclear power is it will run round the clock. It will generate baseload power 24 hours a day, 7 days a week, 52 weeks of the year. That's a big advantage. And these technologies are there, ready to take off the shelf pretty well. Some of these other alternatives of renewables, in many cases they still require a considerable period of development to get them to a stage when they can pay off. So that's the current status. Now, there are, in these so-called Generation 4 reactors, there are a number of other interesting designs. There's the so-called pebble reactor, where the nuclear fuel is encased into spheres the size of tennis balls, and you put something like 1,000 of them into a container, and of course they irradiate each other and start a chain reaction going, and you pass helium gas, cool helium gas, in at the bottom of this container, and the helium gas comes out of the top hot because of the fission. So this reactor can be built. It's much more compact, it's much smaller, but it will generate a considerable amount of heat energy in essentially a safe way. So the design of reactors has not stayed still. We're still developing, and many of the constraints which applied 20 or 30 years ago, these constraints are gradually being overcome and eliminated. So when people come on the box and start banging on about nuclear power and the getting rid of the waste, well, the nuclear engineers have worked on that, and we've reduced the amount of waste that we need to generate. So in future, nuclear power plants can be considerably more efficient than they have been in the past. I think that's probably as much as I want to say at the moment. So that deals with nuclear reactor design. It's only a very brief sketch from the start to the present. But as I say, the new Hinkley Point C reactors will incorporate many of the lessons that were learned at Fukushima Daiichi. It's worth pointing out, incidentally, as well, in the 2007 and 2009, the Japanese, two of their nuclear plants were hit by powerful earthquakes. One was a 6.8 and one was a 6.6, I think. The Fukushima Daiichi one was a very strong one. It was a magnitude 9 on the Richter scale. But the Japanese had two power plants that were hit by very powerful earthquakes, and there was no release of radiation. So people who say, nuclear power is unsafe, the main deaths due to nuclear power are really the deaths resulting from Chernobyl. There are very few apart from that. You can design a plant. All you need to do is install an accelerometer, which will pick up the earthquake as soon as it arrives. This can be connected to a control circuit, which then withdraws the fuel rods, brings in the control rods, and shuts the reactor down. So you can make a nuclear reactor perfectly earthquake-proof without any great difficulty. The problem at Fukushima Daiichi was the accompanying tsunami, which caused a lot of problems. But of course, in many parts of the world we don't have tsunamis, so we don't in Britain. But nevertheless, if the Hinkley Point station is built, it will be one of the safest, if not the safest, nuclear power plant in the world, because it'll be bang up to date. So that's it as far as reactor design.